Hello, this will be a short video on multiple regression, the introduction of regression analysis. And in this video, we'll just spend a little bit of time outlining the concepts of regression and a few basic terms as we move forward. So multiple regression analysis then is a statistical technique that we will use to help try to explain, predict, or otherwise forecast a single dependent variable with several multiple independent or predictor variables. The traditional numeric model that we will estimate is often written like this, where we have a y that represents the dependent variable, and then a series of x variables, which are our indicators or independent variables. The b's that are in this model are estimated coefficients, so we sometimes call those betas. In this example, we have the number of credit cards as a dependent variable, and then we have a series of regressors here, like family size, income, and then the associated betas that would go with them. We may also include a number of other ones here. So this could continue on and on. The other thing that we will have when we write out a model is we will add this error term right there. So that will be some type of a prediction error or residual that will be there. When we actually estimate the model with real numbers, we won't have this. This will not be something that's estimated, but we know it exists and we know it's there. So in the theoretical model, which we see here, we'll keep that in place. The combined formula here, if you will, is the variate. So the variate of y, or the variate that is being computed, would include the entire linear combination of the entire set of variables. And in this case, we want to achieve the best statistical objective. And in regression analysis, in linear regression anyways, that statistical regression will be to reduce our residual or reduce the error that is created. So we have our y, which is again the variate, and then we have a series of x's which serve to create the variate, create the predictive model that helps predict the variance that is observed in y. So the variate then includes a linear combination of the entire set of variables, again, that best achieves the statistical objective. Therefore, our goal is to identify independent variables that are measurable, that are reliable, and that occur without or independently of the dependent variable. So these are variables then that we would expect would occur, but not as a result of the dependent variable that's happening there. Okay, so in doing so, as we do this, we would want to then identify the best independent variables and the best combination of them that explains the most amount of variance in the dependent variable. So in other words, what we want to do is we want to explain the dependent variable, and at the same time we want to minimize prediction error. That will be the key. So some terms we'll use. R squared is a key term that we use. It's also known as the coefficient of determination, and it helps assess the fit of the model and the prediction accuracy. We have things called unexplained variance. So this is variance that in the dependent variable that we cannot explain with our independent variables. So this would be some type of a residual or an error or a leftover amount of variance. We want to minimize that as much as possible. We have an adjusted R square, So an adjusted R-square is the R-square that we have before here, but it needs to be adjusted based on covariance that exists between independent variables. Okay, so we want to be able to explain the dependent variable with as few independent variables as needed, but we also want to be able to explain it with as much accuracy. So what we don't want to do is just add independent variables to blow up the model unless we can use those new independent variables to explain a whole lot more error or variance, variance in the dependent variable. Okay, so then we also have, so other terms here, the SEE, the standard error of the estimate. So the standard error of the estimate is again a measure that we want to think about when we look at the accuracy of the predictions. It's the variation in the dependent variable values around a regression line. We want to, again, if we add values, if we add independent variables, we want to be able to minimize that. And if we can't effectively minimize that, then we're not really achieving our goal. So minimized standard error or error of the estimate, that's what we want to do while we increase our R and R squared. And adjusted R squared. Other terms that we'll see, total sum of the squares, sum of the squared errors, the SSE, and then the sum of the squared regression. Okay, so the key term here I want you to make sure you remember is the sum of squared errors. It's the variance of the dependent variable not accounted by the regression model. It is the residual. The objective here in what we're doing is to obtain the smallest possible sum of squared error as a measure of prediction accuracy. So if we look at a set of data and we have a y that's being, we have a y here that's being predicted, and we have an x here that is what we are using to help predict y. We notice that these observations in the yellow dots are fairly they have a clear pattern. So we would say that these two variables are probably correlated fairly strongly, and they're positively correlated. And so if we fit a line that goes along the blue line, that would be the regression line. And what we're looking at is the difference between each observed observation, actual observation, and what we would have predicted if we had used a formula to do so. So we did a regression. Let's assume we did a regression here, and we see that there's a little bit of a difference between each one of these spots and the actual line that was fitted. We want to minimize this to the best of our ability. We want the software, the regression, to minimize this distance. So the deviation between the actual observation and the fitted observation is what is not explained by the regression. It is what we might think of as the error or the residual that's there. Okay, so that's one example. Here's another example, again, using expense, research and developing expense, and sales. Apparently, the more you do research and development, the more you increase your sales. These are positively related. There's an R square here of 0.69. So we have, there's a constant, and the constant would be where this line crosses. So it's somewhere around 9.15. So we have a constant there. You do not have to always use a constant, but we have one here, and then we have the beta, the coefficient here, 3.4594. When we multiply an x value by that, we get a corresponding y value, which would fall along this this dark line in the middle. So again, our goal here is to fit a line that minimizes the distance between our actual value and our fitted value. That's the goal that we're shooting for. So the least square criterion then is the objective of our research, of this type of research, or this type of regression, of least squares regression anyways. So we want the fitted solution then to minimize the squared error of this variate. So if we look at the actual value minus the fitted value, sum these up, square them, and that's what will be minimized in this process of running the regression that we have. Now, the actual concept of regression is probably the first thing that we do when we do regression analysis, right? So, or statistics in general. So when we learn statistics initially, regression is something that is taught first time, right out of the gate. So it's something that everybody is familiar with, probably before many other advanced statistical techniques. It's robust. It does require normality of data, but it's very forgiving in a lot of ways. And what's actually important to know is that regression concepts, the concept of building a regression, is used in many applications. And so there are lots of adaptations, lots of different considerations. So typically we do regression with metric independent variables, right? So the y variables, the independent variables, are usually metric, but they don't always have to be. So for instance, you could use a dummy variable. So you could use a non-metric item as an independent variable. So for instance, we could put in like gender, or which would be a 1 or a 0 for male or female or whatever. Or we could do bought in the past. Buying something in the past is a great predictor of whether somebody will buy in the future. So they either bought in the past or they didn't. That's a 1 or a 0. That's a dummy variable that's used as non-metric. So you have to use a dummy variable if you're going to use a non-metric independent variable. But regression is flexible enough to do it. Eventually, we'll see where we can also use non-metric dependent variables as well. Again, in a dummy variable sense, if we had the dependent variable be an outcome of like purchase or not purchase, we're trying to predict whether someone will purchase or not, then we can do that, and it's called logistical regression. It's also a variation of that is probabilistic regression. So a probit model and a logit model are two things that we can do that would allow us the flexibility of using a non-metric dependent variable. We can also fit regressions using nonlinear terms, so quadratics. Here, for instance, we have an exponent, which we can build into our variate. So this actually uses, you could use y, and then you could use the square of y, or y squared rather, excuse me, as part of the model. So that will account for some nonlinear elements that y may have. We can use time series. Time series analysis actually has multiple components. It has the trend. It has it has the cyclicality, and then it has seasonality, which happens on a very short basis. So there's actually 3 terms that are used that are built into a time series analysis, and these are not normally distributed. So we're having some exponents and things like that go on. So it's a deviation, but an extension of regression. We can do nested regressions, no question about that. So we can have a regression within a regression within a regression to form our variates. And we can also do things called mediation and moderation. And in particular, moderation. We'll talk about that later at another time. But that's where we have one factor that or one factor or one variable that impacts the relationship of two others. So if we have A and we know that A helps predict or explain B, then that could be like a regular regression that we're running, something like that. But we also may have another variable that gets bumped in here. We're going to call this variable C, and C influences this relationship somehow. That's called a moderator. C moderates the relationship between A and B. B in this case may be our Y dependent variable, X, or A may be an X, and then C is going to be something else, and we'll actually calculate that. It'll be whatever it'll be this X. This is X1, let's just say. So it'll be X1 times, and C will be another variable, X2 we'll call it. Okay, so that'll be how we form our moderator. Okay, so again, I think the important idea here is that regression is a fundamental kind of practice, I guess. But the beauty of regression is it's extremely flexible. We can do many, many, many different things with regression, so that's what we need to think about doing. Number of stages can happen when we're looking into regression. So first of all, we need to be able to be comfortable with the objectives and what we want multiple regression to do for us. Then we need to design our regressors, and we need to know what independent variables we're going to use and whether they're metric or not. We need to verify our assumptions, which will be non-multicollinearity. So we need to look at the correlations between independent variables and make sure that things are as linear as we can get them and normally distributed as we can get them. Then we need to go ahead and run our regression estimating the model. Then we have to interpret the fit. Make sure we understand what the variate is telling us, and then confirm that our results are valid. So this is basic research. I mean, these are the steps that you would find in a lot of research techniques. So these shouldn't be too outlandish to think about. Key things we want to make sure we're doing is verifying that our assumptions are strong. Make sure that the independent variables we're using make sense and that they seem to be reasonable in explaining the dependent variable and looking at the fit. We want to make sure that those things all strike a good balance. Okay, so just to wrap this up, when we look at the first stage, or just thinking about the objectives then, in selecting a suitable application for multiple regression, we want to consider what the primary use of multiple regression is. We want to make sure that when we do multiple regression, it's appropriate for the type of research that we're doing. That we are looking to specify a relationship between variables. So that's kind of a key thing, and we're actually doing some significance testing here. So when we do significance testing, we may have some hypotheses, but we may also need to require some theory. So what we are actually saying when we create a variate in this, when we have these variables that go like this, we're actually saying that these X variables are contributing to, maybe causing, or even leading to this Y. So theoretically, does x1 and x2 precede y in action? Is there statistical significance in the relationship between x1, x2, and y? Does it make sense that x1 and x2 actually cause y, theoretically and just on the surface? So that's kind of, I mean, we are making the statement that x1 and x2 cause y when we do this, and we're going to prove this statistically, and we're going to test to see if this beta is significantly different from 0 to confirm our suspicions. Okay, so that's what we are really shooting for when we're looking at this primary use concept. So we're absolutely talking about prediction. We want to maximize the overall predictive power of our variate, and we can do this by running multiple models using different deep independent variables and trying to clean up those variables as much as we possibly can. But we also want to specify not only what independent variables predict the dependent variable, but the relationship they have as well. So like which y variables, which independent variables are more important than others? That's a good question to know, and so that's one of the things that we'll want to do. So we'll want to assess those relationships. We'll want to be able to gain some insight between the interrelationships between the y variables, and in general, just be able to understand what the predictions are actually telling us overall. Okay, so again, wrapping this up, we want to be able to summarize our data once we are done with this regression. We want to be able to make predictions. We want to be able to interpret our coefficients. Okay, those things are paramount for us to be able to do. So forecasting may be something we're wanting to do. We want to be able to change our dependent variable. So like, for instance, if I want to predict the likelihood of sales, somebody will buy a product, or I want to predict sales, if I know what goes into creating sales, then I can change my sales. So I know advertising expenditure has an impact on sales. So I want to know how much of an impact, and then I can increase advertising to reach a certain sales point that is important to me. So it allows me to predict things, but it also allows me to use the coefficients to actually make managerial decisions. So we lean on theory, we lean on experience and knowledge of the variables to create a realistic variate that we're going to test. And then we're going to run the model, and remember that regression is all about minimizing error, whether it's specification or measurement error that we may have. We want to minimize the difference, the residual difference between our predicted value and actual values in order to create a strong representative model. Okay, so this is an introduction to regression, and thank you so much for spending time with this video lecture, and if you have any questions, just let me know.